Dear students, I welcome you all for our lecture series on food technology. In today's lecture, let's make an attempt to know about water. Water is an important basic element in all foods. Water is called as the universal solvent and it is a basic necessity for the growth and metabolism of microbes and various chemical reactions that occur in food products. Water occurs in food systems as free water and bound water. Water is found as an intracellular and extracellular component in foods. The importance of water as a crucial component necessitates the understanding of the properties and behavior in food systems. The way water behaves in foods can provide information on the stability of a product as well as its shelf life. The following topics will be dealt in this chapter. 1. Definition of water in food. 2. Structure of water and ice. 3. Types of water. 4. Water activity and sorption phenomena. 5. Water activity and shelf life. And 6. Water activity and packaging. Now, let us start with the definition of water in food. Water is a chemical compound composed of 2 hydrogen atoms and 1 oxygen atom. The liquid state of this compound is termed as water, the solid state as ice and gaseous state as steam. Water is also the most substantial component of foods and acts as a medium by supporting chemical reactions. Water has an important role in the stability of most of the food products. The quantity and characteristic of water present in the foods has an impact on the chemical processes of value in terms of food safety. The physical and chemical stability as well as growth of microbes in a food can be controlled by optimizing the water within foods by various methods. Water content of a food product alone cannot provide a view of the potential microbial response and chemical reactions, even though it is the most widely discussed concept in terms of water content of foods. Water content is measured by drying, infrared or nuclear magnetic resonance techniques, but the measure of water activity along with the total water is essential to describe its water status. The measurement of water activity is more relevant in understanding the quality and safety aspects of water. Let us move on to the next topic, structure of water and ice. The function of water can be understood better when there is clear knowledge about its structure and the state it occurs in a food system. The first concept, physical properties of water. Water exhibits various physical properties which can be understood on comparison to the properties of molecules similar to water. The physical properties of water are presented in table number 1 on your screen. Water appears to have a high melting point of 0 degree Celsius and boiling point temperature of 100 degree Celsius. There is also a considerable difference in the density, vapor pressure, thermal conductivity of water at 0 degree Celsius and 100 degree Celsius and ice which further changes on freezing. The thermal diffusivity, which is indicative of the rate at which a material can undergo a change in temperature or the rate at which heat moves inside a compound is 9 times higher in ice than water. This change causes freezing of water at a rate 9 times faster than thawing. So, the reason for the unusual behavior of water and ice can be further understood by their chemical structure. Let us know the structure of water and ice. Each molecule of water is composed of 2 hydrogen atoms and a single oxygen atom. Each hydrogen atom is bound to the central oxygen atom by a pair of electrons, which is usually termed as a covalent bond. There are 6 electrons in the outer shell of a water molecule, out of which only 2 are engaged in covalent bonding. The remaining 4 electrons tend to be arranged far from each other to avoid or reduce the repulsion due to the same charge, thus providing a tetrahedral geometry. Since the 2 pairs of free bound electrons remain closer to the oxygen atom, they repel the electrons in the covalent bond, thus pushing the 2 hydrogen bonds nearer to each other, resulting in the arrangement of hydrogen and oxygen atoms at an angle of 105 degrees as shown in figure number 1 on your screen. If you look at the figure, we can see the 2 hydrogen atoms are arranged towards the right side of the oxygen atom, and the angle between them is at 105 degrees. Also, we can see partially positive side of the water molecule, which means the right side of the molecule has positive charges. Positive charges are due to the hydrogen atoms which carry a positive charge, each one of them. Ice has a well-defined structure where each water molecule is surrounded by 4 neighboring water molecules. 2 water molecules are bound to the oxygen atom directly and other 2 are bound to the hydrogen atoms as shown in figure number 2 on your screen. In figure number 2, where structure of ice is depicted, we can see there is bonding between 2 water molecules with the oxygen atom of the third water molecule through the 2 hydrogen atoms. This bridging breaks when ice melts, leading to the formation of water in a liquid state. Now, let us learn the types of water in foods. Water in food and products can be discretely classified into 2 forms, namely bound water and free water. Bound water is that part of the total water bound by water soluble compounds such as sugar and salt or substrates that can form a matrix, thus making it unavailable to any physical, chemical and microbial activity compared to free water, which is the proportion of water inside foods that is available for such chemical reactions and growth of microbes. Major proportion of water is in the bound form, that is bound to ions or bound to surfaces of large molecules or cell structures. The measurement of the intensity of binding of the water molecule is important in predicting the reactive nature of water in foods. The free water has the ability to support microbial growth and participate in chemical, enzymatic reactions and spoilage activities. Thus, the amount of free water is more important for understanding and analyzing the chemical and microbial stability of a food than its total water or total moisture content. Water content in foods can be measured by gravimetric method, where the food is dried till the moisture content is evaporated fully, followed by measurement of the dry matter. Karl-Fischer titration, which involves the reduction of iodine by sulfur dioxide in the presence of water. Now let us learn about water activity and sorption phenomena. Water activity, in short denoted by AW, is defined as the ratio of the vapor pressure of water in a substance to the vapor pressure of pure water. It is calculated using the formula AW, or water activity, equals P divided by P naught, where AW is the water activity of a food, P is the partial pressure of water in a substrate, and P naught is the vapor pressure of pure water in the same temperature. Water activity defines the efficacy of water in the food to take part in chemical reactions. The extent of unavailability has a negative impact on the water activity. In other words, higher the proportion of bound water, lower will be the water activity. The tightly bound water has less chances of escaping the food as vapor, thus is devoid of partial pressure. When the partial pressure is 0, the water activity will also be 0. Water activity ranges from 0 to 1, where 1 is the water activity of pure water. The water activity of a food will be closer or equal to 1 when the amount of moisture in it exceeds the solid content, whereas water activity will be lower than 1 when the solid content is more than moisture content of a food. The water activity is dependent on the temperature, boiling and freezing point, equilibrium relative humidity, and osmotic pressure. Relative humidity of a food product is the humidity of air surrounding the food. When this is in equilibrium with the environment, it is known as equilibrium relative humidity, abbreviated as ERH, at which the food product does not gain nor lose water. When the relative humidity increases than the ERH, the product gains moisture. When the relative humidity decreases below ERH, the product loses moisture and becomes drier. This confirms the relationship between ERH and water activity, as both are based on vapor pressure. ERH is dependent on the chemical compound, temperature, water content, storage conditions, absolute pressure, and packaging. Water activity can also be derived from ERH using the following formula: AW, or water activity, equals equilibrium relative humidity divided by 100. The process of adsorption and desorption are not fully reversible. Thus, the isotherms of each of these can be differentiated based on analysis of increase or decreasing moisture content of a food product. On adsorption, the product becomes wet or gains moisture, and on desorption, the product becomes dry or loses moisture. Adsorption and desorption isotherms are used for observation of hygroscopic products and the process of drying respectively. Water sorption isotherms usually have a sigmoid shape curve, which is attributed to the presence of 3 types of water. Water type 1, strongly bound monolayer of water molecules; type 2, weak but hard to remove multiple layers of water, and type 3, loosely bound multilayered water condensed in the capillaries and pores of the food material. The typical shape of water adsorption and desorption isotherm is shown in figure number 3 on your screen. As you can see in figure number 3, the rate of water activity is lowest for water type 1, whereas it is highest for water type 3, and overall both the curves for adsorption and desorption show a sigmoid type of curve. The shape of the moisture isotherm typical for most foods is shown in figure number 4 on your screen. So, if you look at figure number 4, which is representative of the typical moisture isotherm for most foods, again we can see a sigmoid shape curve with higher water activities when the water is of type 3 or loosely bound water, and water activity at the lowest when the water type is type 1 or highly bound water. Hygroscopic foods can have a steeply sloping curve, whereas foods less sensitive to moisture or non-hygroscopic can have a flat curve as shown in figure number 5 on your screen. If you look at figure number 5, we can see 3 types of curves. Curve B represents the typical moisture isotherm for most foods. Curve A represents the curve representative of non-hygroscopic foods or anti-caking agents, and curve C represents hygroscopic foods or foods that gain moisture when exposed to air. The definition of conditions favoring the growth of microbes is of utmost importance in the food stability and food preservation process. Water activity can predict safety and stability with respect to microbial growth, chemical and biochemical reaction rates, and physical properties. Microbes have a critical water activity level below which they cannot grow or multiply. Growth of bacteria is inhibited at water activity less than 0.75. Growth of all microbes is inhibited at water activity less than 0.6. Maillard reactions or browning occurs at a maximum rate at 0.6 to 0.7 level of water activity, and inactivation of enzymes occurs at less than 0.75 water activity. Preservation of B vitamins such as vitamin C, fat soluble vitamins such as vitamin E and thiamine is observed at a lower water activity. The graphic representation of the reaction rates of the above discussed variables at various water activity levels is shown in figure number 6 on your screen. In figure number 6, you can see a typical moisture isotherm denoted in between, whereas towards the right side of the curve or right side of the graph, we have levels of water activity or curves of water activity denoting each microbes. One to start with bacteria, yeast, then molds. Then there are also curves depicting water activity of non-enzymatic browning as well as lipid oxidation. As we can observe, at water activity levels less than 0.6, there are no evidence of growth of any kind of microbes. The measurement of water activity can be done by using a resistive electrolytic hygrometer, capacitance hygrometer, or a dew point hygrometer. The principle involved in these hygrometers involves measurement of change in temperature, pressure, mass, or a mechanical or electrical change in a substance as moisture is adsorbed or desorbed. Now, let us move on to the next topic, water activity and shelf life. Changes in the water activity by absorption of water when a product is exposed to a high humidity environment, or loss of water when placed in a low humidity environment can cause undesirable changes in food products and can shorten the shelf life. Physical changes include loss of crispiness in dry products, caking and clumping of powders, and loss of water from moist foods, making them sticky. Other undesirable changes are acceleration of chemical deterioration or microbial growth. Moisture content and water activity affect the progress of chemical and microbiological spoilage reactions in foods, which is discussed individually one by one. So, the first one, microbial growth. The shelf life of a product is an important aspect of food safety. Stability of a food depends on the water activity and pH in the food environment. Foods with higher water activity are highly perishable. Microbes able to cause food deterioration need certain conditions for growth, namely available moisture, optimum pH, the right temperature and nutrients. The growth of microbes can be checked by controlling these factors, and shelf life of a product can be increased. The shelf life of a food can be determined based on the ingredients used, pH, water activity and microbiological inhibitors. In general, bacteria require higher values of water activity for growth compared to fungi and gram-negative bacteria, which require higher water activity than gram-positive bacteria. Dried or freeze-dried foods have good shelf life and stability because their moisture content is between 5 to 15%. A moisture level of 20 to 40% and water activity of above 0.5 is found in intermediate moisture foods such as cakes. Refrigerated foods are especially vulnerable to microbial spoilage, thus reducing their shelf life. They are at a higher risk of deterioration by microbes and may sustain pathogenic microbial growth. The growth of microbes in food can be monitored by microbiological methods. Reactions such as gas production, syneresis, and changes in color or viscosity can also indicate changes in the stability of the product. Now, let us have a look at the chemical deterioration of foods. Water activity influences chemical and enzymatic reactivity apart from microbial spoilage. Water may influence chemical reactions by serving as a solvent, reactant, or by changing the mobility of the reactants by altering the viscosity. Chemical deterioration of packaged foods can be due to three major reactions in food, namely oxidation of lipids, enzymatic degradation, and non-enzymatic browning. These reactions can occur simultaneously in foods, and their rate is accelerated by increase in storage temperature. Monitoring the level of lipid degradation products at elevated temperatures is one of the principal methods used in predicting the shelf life of a product. Lipid oxidation at these temperatures can occur due to the action of free radicals, enzymatic action and oxidation by light leading to the formation of hydroperoxides. Free radical synthesis is catalyzed by heat, light or metal ions, for instance copper ions. Free radicals generated by oxidation reaction result in peroxides that are further converted into alcohols, aldehydes, ketones and free fatty acids. Many of these compounds have strong flavors and odors referred to as rancid fat. The double bonds of unsaturated fatty acids, mainly oleic, which has 18 carbon atoms, linoleic acid, which has again 18 carbon atoms and 2 double bonds, and linolenic acid, which has 18 carbon atoms and 3 double bonds, are the targets of oxidation. The rate of oxidation occurs 64 times faster in linoleic acid and 100 times faster in linolenic acid on comparison with oleic acid. Photosensitive compounds found in foods such as riboflavin, chlorophyll, myoglobin, heavy metal ions, etc. are excited to a high energy state on absorption of light. This energy reacts with the oxygen atoms and forms highly reactive singlet oxygen, which can cause oxidation of fatty acids, leading to the formation of singlet oxygen in the formation of hydroperoxides. Majority of the enzymes in food are inactive when the water activity falls below 0.85. Such enzymes include amylases, phenol oxidases and peroxidases. Lipases can remain active at a water activity value at 0.3 or 0.1. The enzymatic action of lipase with triglycerides in food leads to the formation of free fatty acids, resulting in rancidity. These fatty acids have distinct flavor, such as lauric acid, which has a strong soapy flavor detectable at concentrations of even 0.3%. Other fatty acids found in vegetable oils that are capable of producing off flavor at 2% concentration. Another example is butyric acid found in rancid butter, which is capable of producing rancid flavor at minimal concentration. The non-enzymatic browning or Maillard reactions are one of the most important factors leading to food spoilage. The water activity favoring this reaction is between 0.6 to 0.7. Browning reactions are slow at low level of humidity and are seen at maximum rate in intermediate moisture foods. Other chemical reactions influenced by the water activity are hydrolysis of protopectin, splitting and demethylation of pectin, autocatalytic hydrolysis of fats and the transformation of chlorophyll into pheophytin. Now, let us understand the relation between water activity and packaging. Water activity is a critical factor in determining the shelf life of products. The upper and lower water activity levels can be established keeping in mind the microbial, physicochemical and nutritional characteristics of food products. The shelf life of a packaged food is determined by the rate of exchange of moisture through the package and rate of change in water activity. Data on the temperature, relative humidity and critical water activity values will aid in selection of a packaging technique and optimize the quality and shelf life of a product. Sorption isotherms have an important role in the selection of packaging materials. Hygroscopic products always have a steep sorption isotherm. Such foods require packaging material to be moisture proof, for example, glass containers with waterproof seals or thick polyvinyl chloride material. Instant coffee, for example, loses its flowability and cakes at critical limit of 50% relative humidity. Non-hygroscopic products can be packaged in polyethylene containers as reactions do not occur at normal storage conditions. For some foods, the equilibrium relative humidity is more than the external climatic conditions. Such products require the packaging material to avoid the loss of moisture. Examples of such foods include processed cheese and baked goods. Thus, we can conclude that water, apart from being the most important constituent of food, has a crucial role in the stability and safety of a food product. Water and its behavior in food systems can direct many processes that can dictate the shelf life, microbial safety and sensory characteristics of a food product. Water activity of foods needs to be controlled based on the nature of the food product by optimum packaging materials and storage conditions. Thank you.